Okay, so the last thing that we have to touch on, it's actually not too bad. I know last time we ended with resonance, which was the hardest portion of the week. This is actually not too bad, this concept of Lewis acids and bases. So everything we've been working with up until this point is this Bronsted-Lowry definition of acid bases, where an acid is a proton donor and a base is a proton acceptor, right? Then this dude named Lewis came along and he expanded the definition of acids and bases such that a Lewis acid accepts and shares electrons. Okay, so it doesn't just donate protons, it accepts electrons, whereas a base donates and shares electrons. This is not inconsistent with the Bronsted-Lowry definition. Every Bronsted-Lowry is a Lewis, every Bronsted-Lowry acid is a Lewis acid, and every Bronsted-Lowry base is a Lewis base, but it expands it even more. So here's an example of both a Lewis acid base reaction and a Bronsted-Lowry base reaction. And let's just convince ourselves that this all makes sense. Hydrochloric acid, this would be our acid, this is our base in our standard definition, so let's just see how it checks out with the Lewis definition. So according to the Lewis definition, an acid should accept, let's actually do this in a different color, an acid should accept a pair of electrons. So here is our acid, and it is indeed accepting a pair of electrons from that base. Likewise, a base is a molecule that donates or shares a pair of electrons. That's exactly what's happening here, right? So it's kind of like just a different way of thinking about this. So why the heck did they bother to expand it? Well, because it turns out that there are some Lewis acids and bases that aren't Bronsted-Lowry acids and bases. So let's see a common one here. Boron is a great example of something that's going to be a Lewis acid. Why? Because boron has 2, 4, 6 electrons in its octet, and it can accept 2 more to get to 8. Okay? So that's exactly what happens in this case here. This is actually my Lewis acid. It's accepting a pair of electrons from this Lewis base here. Okay, and there's no exchange of protons or anything like that that's going on. This would just create a new bond, right? So this is this new bond being created here, and then of course charges we all got to pay attention to. Boron's now got an additional 2 electrons in its octet, which then adds 1 electron to the formal charge, so that's a formal charge of -1. Oxygen's got 3 bonds in 1 lone pair, so that's a formal charge of +1. Okay. One of the reasons why we bother to teach you guys this is because this is a pattern that we're going to see over and over and over again with an electron-rich species interacting with an electron-deficient species. That might not be how you spell deficient. I don't know. Not a speller. But it's just an expanded definition of an acid-base reaction. So other common Lewis acids that are not Bronsted-Lowry acids that you're going to see are iron 3 bromide and aluminum chloride. They also sort of characteristically are involved in these types of reactions where they're accepting pairs of electrons. And same thing, they all have 6 electrons currently in their octet. By accepting 2 more, they can get to 8. So that's kind of the motivating force there. But importantly, you just want to be able to identify, given an acid-base reaction, a Lewis acid-base reaction, who's the Lewis acid, who's the Lewis base, and then being able to draw these sort of mechanistic arrows. So that's what your practice will be. Okay? So not too bad. It's just sort of more terminology, and we'll see. I think, to be honest, I think it's always a little weird to put this in the acid-base lectures. They are in every textbook you'll ever see. But the real thing is that we'll see this pattern over and over again with every reaction that we ever see. Electron-rich species react with electron-deficient species. And I think it's just a good illustration of that, which is why it's put in there. Okay?